We live inside a constant, invisible hum of electromagnetic energy. Radio, Wi-Fi, and cellular signals saturate the air, passing through us at every moment. But in a setting like the Rohingya refugee camps in Bangladesh, that energy exists in a total infrastructure vacuum. There is no traditional power grid here, no lines bringing electricity to these shelters. For the people living here, information functions as a literal form of aid. Critical security alerts, vital health updates, and aid distribution schedules are the difference between safety and catastrophe. Most communication tools rely on batteries, but batteries are expensive. They leak toxic chemicals into the ground, and in a crisis zone, they are a finite and exhaustible resource. When the power runs out, it creates a silence that isolates thousands of people, even though they are physically standing in the middle of a dense field of broadcast signals. The air in these camps is already vibrating with the exact radio waves carrying the information they need to survive. The challenge is designing a receiver that can physically extract its operating power from those same invisible waves. This is the logic of energy autarky. It moves away from centralized power and toward a system where the information-carrying signal provides its own electricity. Marika Gast addressed this challenge in 2005 with the refugee radio, an industrial design engineered specifically for environments with limited resources. The device is built for frugal manufacturing. Its paper packaging is a functional part of the design, serving as both the instruction manual and the radio's permanent housing. Making a device run without a battery requires capturing and converting ambient radio frequency energy, a process rooted in the foundational experiments of the 19th century. In 1888, German physicist Heinrich Hertz provided the first experimental proof that electromagnetic waves could be produced and detected in a laboratory. Decades later, Arno Penzias and Robert Wilson used this massive horn antenna to confirm that the entire universe is saturated with ambient microwave radiation, a permanent background noise left over from the dawn of time. These discoveries established that our environment is a permanent reservoir of invisible energy. Harvesting that energy requires a rectenna, a circuit designed to capture a signal and turn it into usable electricity. The antenna component intercepts the electromagnetic wave, which induces a microscopic alternating current inside the circuit. Because ambient signals are so weak, they cannot pass through standard silicon diodes, which require a relatively high turn-on voltage. Instead, these circuits use Schottky diodes, which have a much lower threshold for allowing current to flow. This diode acts as a rectifier, converting the oscillating AC wave into a stable, unidirectional direct current. Additional components, like charge pumps, act as a funnel, stepping up the voltage stage by stage until there is enough pressure to drive a high-impedance earphone. This chart illustrates the primary limitation of the technology, the inverse square law. Power density drops off drastically as you move away from the source, meaning the available energy is measured in tiny microwatts. These physical constraints mean radio harvesting can only support ultra-low power devices, like earphones or small sensors. It isn't currently capable of driving a high-volume loudspeaker. For people in a refugee camp, that tiny amount of power provides a permanent, maintenance-free connection to health and security networks. Access to self-powered hardware also enables the growth of community-led media. Groups like the Refugee Radio Network can reach listeners who no longer have to worry about the cost or availability of batteries. The engineering used in these humanitarian contexts is already moving into consumer products, enabling radios for remote cabins or hiking gear that will never need a recharge. With the rise of 5G infrastructure and flexible printed electronics, we are approaching an era where millions of small, autonomous Internet of Things devices can run indefinitely without a battery. By solving the problem of communication in the world's most vulnerable environments, we are learning to treat the electromagnetic spectrum as a reliable, ever-present source of energy for our most vital